scan. I'm not going to ask you to scan in the lab packets with the outcomes. I kind of like it because I can actually see the data with the write-up, which is kind of nice to see what internal consistency or whatnot. But either hand it in or at least let me check it off at some point before you leave, so I can make sure it's complete. It's pretty much 5 gimme points, unless it's not complete. So if missing things or just really crappy analysis, not the data necessarily itself, that tends to be what it is for various reasons, especially in electrostatics lab. This room is really horribly dirty in terms of dust. So electrostatic labs are always a little bit tenuous. However, how you analyze the data and the parameters that you get is still fundamentally important. So, to the extent that you're actually processing the information and appropriately analyzing it, that's what I'm concerned with. But it's pretty much gimme points. The other side of it is a lab write-up. I don't need a notebook, I don't need a big, long dissertation, but basically a 1 to 2 page summary. And the summary will have 3 parts. The 3 parts are listed explicitly, including an example write-up, which please use as at least a template in the lab requirements packet. By this time, I'll take a certain amount of solace in knowing the fact that you've done some error analysis in 211, 212, so I'm not too worried about going over that stuff, not points, pages. And the key ideas are a theory, not a procedure, a results section, short and sweet, and then a summary that ties the results and the theory together. Okay? Cohesive, complete. Don't just put a bunch of litany of information down if it doesn't tie together, then it's not particularly useful. Theory's worth 2 points. The result is worth 1, results potentially, and the summary is worth 2 points as well. Okay, so typically this is where where all the plus or minuses in your lab grade come from. I tend to be much more punitive for missing elements in the lab summary than I am clearly in the lab activity packet itself. So just the key is 2 or 3 paragraphs in terms of the theory and the summary, but just be complete in terms of what it is we're looking at, electrostatics, charge separation this week, and really the phenomenon of electric charge, and how the theory, as a general idea, is going to be explored in the lab. Because ultimately your results ought to reflect the application, or at least the outcome of that application. Again, most of you have seen the spiel and whatever, but I just want to sort of point that out. Any questions between now and then, just let me know, or if you want to submit it early so I can take a look at it and make comments. That's okay. I'm not trying to leave you out on an island. I want you to know what I'm looking for, because mostly I just want thorough, concise, organized dissemination of that particular activity is all. Nothing deeper than that. I don't need adjectives or a bunch of other crud. So that's pretty much it. Like I said, any other questions? What I will mention though, just as an aside, a lot of experiments, you may use Excel, for instance, to do some of your analysis. If you've got like tables and trials of data, but you're doing the same type of calculation, you may just use Excel to do that. You might as well just cut and paste the data table at the bottom of the lab summary. Now, most of the time that information is in the packet. I don't think this week, but usually there's a data table sort of included in the write-up. Well, it's fine if it's there too, but if you're typing it in anyway to do some calculations, you might as well include it. Because if you send it to me in digital form, it's not any extra paper as it is. But it does allow me to look at it. And really that's the key, is I want to be able to kind of look at your data too. Oftentimes if a result is screwy, I can kind of see, oh, you might not have done something over here, but I can't tell if I'm just looking at the summary and I've already looked at your packet separately, because I don't have the memory to do that. Also, please include just a digital version. Just cut and paste your files, or I'm sorry, your graphs that you create. Just cut and paste them. You can maybe shrink them a little bit from the Logger software that we're using to generate them, or Excel if you're just doing it outside in Excel. But just put those in there so I can look at the graphs in terms of the context of the summary page, just so it's kind of a complete idea. And really, that's pretty much it. Okay. And again, any questions? Yes.
Yeah, if we decide to scan and attach the lab write-ups, the Google documents.
You mean with the packet?
Yeah, with the packets to the write-ups, the digital write-ups. Do you want it to still embed data?
Clearly not necessary. Like I said, the only advantage to doing that is if you're already doing the calculations in a spreadsheet, then it's not even 5 seconds to include it anyway as a cut and paste. But it's no, I don't want redundancy. I'm not too worried about a bunch of extra steps. I'm usually just sort of a straight to the point. I don't want to take the sidewalk around and do a bunch of 90-degree angles. If I want to get to the building entrance over there, I'm probably going to cut through the bushes, and as long as I don't scare somebody coming out of the bushes on the other side, cut through the grass, over the bench, I'm going to get there. And I don't care about all the other circuity. I just don't. I just usually am on time. That's why I drink Folgers in my office. Hate Folgers. But I'm not going to walk all the way to the other side of the building just to use the little coffee machine over there, and then walk all the way back and wait the 2 minutes to brew the little cup in the little thing. It just takes too much time. I have other things to do. Okay, so that's sort of my mindset, is just I just want to get it done. Now I can spend all my time talking too much in here. So things I give and take. So any questions on that? It's pretty straightforward, and because at least 2/3 of the class has already seen it, definitely bounce ideas off, even if you're working in a different group. It doesn't hurt. It's a good thing to collaborate ideas, always. Scientists rarely work in a vacuum, and the ones that do end up getting manically depressed and end up killing themselves. No, Boltzmann did that. Boltzmann did that. Some of it, I'm sure, was biochemical, but some of it was also the stress of developing an atomic particle model of thermodynamics and not having a community of physicists fully embrace the atom hypothesis to begin with. So that becomes a little bit problematic when you're presenting this brilliant work and nobody really accepts it. It's like, okay, that's great math, whatever. So what, right? I mean, really, just, it's so, talk, we're among friends. This should be a good place. This is, So, okay, so that's basically it. Now, today's experiment is focused really on the idea of electric charge. We're not, the lab itself is not at the point of electric forces and all those calculations. It's more just using a simple device, which is an electrical charge sensor. The charge sensor should be in one of the tubs. Well, these guys over here in the southwest corner have theirs out already. In there, now you can see there's a very impressive rabbit's fur, or maybe it's a cat fur, I'm not sure, that we typically use for stroking our rods. But we do have today, I think, some towels that maybe will work better. So, I don't know, we'll try it. These are new kits, so we'll see how it goes. Today's experiment is fundamentally sound, gone through it, but first time with a group of people, we'll see. The charge sensors can be a little bit fussy, so definitely follow the specific directions from the manufacturer. Well, I mean, not the manufacturer, in the procedure as far as using it, because with all the drifty charge in the room, we just want to make sure that we're careful. Because otherwise you can get weird results and have no idea why. You want to be close enough to some metal so that you can run a wire from the ground of the charge sensor to some metal that's attached to the building somewhere. Or even the table, if you can find a clean connection point, just because it's a very large conducting object. So that'll hopefully help. Now, to this end, I just want to focus, a lot of the stuff is in here, but the key idea is, you know, one of the reasons why nature is, for the most part, sort of neutral, aside from the fact that if everything came from nothing but energy, it would require that you have symmetric positives and negatives being produced for every generation of something, anything. That's sort of the idea of the Big Bang, at least in part. Or I guess a bunch of goofy guys looking silly with a kind of a cute blonde next door on TV. I don't know. It's a different Big Bang, I guess. But the idea, though, is that you've got positively charged nuclei and negatively charged electrons, and so you've got that natural association. So aside from the fact that we need this for establishing our basic properties of matter, the other idea is that things just tend to coalesce together by their mutual positive-negative attraction, and certainly push apart by their repulsion. So we've got sort of these ideas built in sort of naturally. Now, there are ways to separate electrical charge, and usually when electrical charge is separated, or when you look at a piece of plastic that's, you know, it's a little bit staticky, the reason why it's got that electrical charge, or that net charge, is because somewhere in its reality, it's either gained or lost electrons from the surface atoms in the material. How that happens, I don't know. It may be because before class, maybe the vigorous rubber, maybe in the manufacturing process it came out of a package. I don't necessarily know, but if there's static charge built in here and it's on this thing, it's because electrons have been gained or lost. Protons aren't really gained or lost. Sort of kind of maybe come to the realization that the attraction in the nucleus and the forces involved that hold nuclei together are so incredibly intense that it's really just not, anything is likely, but very few things are necessarily probable. What happens around us is just sort of the most probable outcome in nature. So to that end, that's sort of what we're left with. It's the electrons, they're the furthest out, and it's those negative charges that tend to come and go from various physical systems. Now, to that end, a couple different ways of physically separating electrical charge. In fact, there's even ways of manipulating electrical charge that don't necessarily involve separation, but we'll focus on separation of electric charge. And the idea is essentially, well, in order to separate an electrical charge, what is it about an electrical charge that makes it interesting, but also makes it potentially not very observable? What's necessary even to see an electric charge? Another electric charge.
Yeah.
Literally, without an electric charge won't do anything. You have no idea it's even there. You need an electric charge in order to observe another one. Sort of a circular situation, but it's the truth. Right? Gravity doesn't mean anything without something pulling on it. So, to that end, to separate electric charge, ultimately you have to use some other electric charge, or system of electric charge, to disturb something in such a way that you can draw off electrons, or at least transfer electrons, negative charges, back and forth. And there are a few different ways, and we'll talk about the various ways in this particular effort, how that occurs. And the easiest that we normally think about, you think about being a kid and rubbing, scuffing your feet on a carpet and zapping your neighbor, is just using friction. Well, what is friction? You're basically disturbing surfaces by applying a normal force, but then creating a tangential movement or a transverse movement between the surfaces. The outcome of that is that if the two materials are sufficiently different in their attraction of the electrons around it, then you have a certain probability of one side of that interaction drawing electrons from the other side. Everything comes down to pushes and pulls, electric force interaction, and where is it likely to go based on how it's disturbed. That's always really what it comes down to. You think chemically about it, but really that's what it comes down to. Non-metals, non-metallic substances tend to attract electrons because they tend to hold them more tightly, partly because of the compressed nature of how the electrons, or the volume that the electrons already there are located or organized.
They want to gain one as well?
Well, to say they want to gain one is probably
They wanna lose one.
the wrong choice of words, but to say it's more stable when it does gain one
Right.
is a little bit more correct. And what did we learn? Hopefully you went and looked a little more further at the experiment the last example on Thursday. Remember, the question was, if you take positive charge and put a negative charge on either side, and you assume that that the electrons are moving in a uniform circular orbit, for a certain amount of force to be required to hold an electron in a particular separation distance from the nucleus, if you put another negative charge in that same circular pathway or region, in order for the attractive force on either of these to be strong enough to hold it in, compared to just having one, it's going to require that they suck in closer to the center. Well, what does that mean? It means that if you've got a positive charge and you've got these things sucked in closer than, say, they would be if you only had one of these and it's out here, then if you have a negative charge over here, the negative charge here is farther away than it would have otherwise been, and it allows the negative charge to be closer to the positive charge, which means that the attractive interaction is greater, and the interaction between these is weaker. Is it enough to matter? Well, it just depends on the situation. The chemistry always comes back to the physics. So as you move along the periodic table to the right, the electron orbitals, or the volumes of the atoms, get smaller and smaller, which means, among other things, that if you have other electrical charges, negatives coming around, they're going to be ever so slightly more attracted than they would be to the nucleus, because they can get ever so slightly closer without the electron repulsion than the corresponding atom that has its electrons out farther. So there's all kinds of these consequences. So what creates stability and what creates this electronegativity or negative attraction? It has a lot to do with having more electrons packed in closer and allowing neighboring or environmental charges outside get closer to the nucleus, and therefore a stronger interaction. And then of course we've got all the quantum ideas that sort of take it completely to another level. But that's sort of the idea. So you rub two surfaces together, depending on the nature of how those electrical charges are spread around, you're likely to have a situation where one side may have a slightly higher attraction or greater attraction to some of those electrons that are interacting than the other side. When that happens, you'll draw some charge over. You may not draw a huge amount, but you'll draw some over. Consequently, one side becomes more negative, the other side becomes more positive. Pretty simple, pretty straightforward. But it oftentimes gets overlooked. So really that's sort of the idea. Different substances, different electrical, physical properties. Another way that this can happen is to take a charged surface, or take a charged substance, and contact. So I take some material, and maybe it's got extra electrons on it. Well, those electrons, if they're excess, are going to be repulsing each other. They're stuck on this surface, they're not going anywhere. But they're pushing away from each other as far as they can because of this Coulomb and negative repulsion, or this repulsion between the charges. So if you take a surface that does not have electric charge, or doesn't have as dense of electric charge, if you make contact, then this repulsion is going to allow the electric charge to spread out as far as it can, resulting in less electric charge here and more electric charge here. Now this becomes net charged, even if it was neutral before, and this loses some of its charge. like a virus. Cooties on your hand, you touch somebody else, now they got. So that's charge separation by contact. And again, it's just this consequence of pushing things away, right? It all comes down to that whole litany of forces, except for gravity, or what's in the nucleus, it all just comes down to electrical force, attraction, repulsion, these darn charges floating around.
So when you're walking across a carpet, what's charged? Is your feet charged or is the carpet charged? What happens?
Depends. Neither necessarily has to be charged, but the rubber on your shoes, if there's any sliding, any scuffing between your shoe surface and the carpet, now you disrupt those electrons. If one side or the other has a stronger attraction, usually the rubber on your shoes has a greater attraction for the electrons because it's more insulating than the carpet, which tends to be a little bit more conducting. Consequently, the charge will typically, the negative charges will typically attract to the surface of the rubber and then ultimately spread out, and then you can go and zap somebody. And then the charge redistributes in the carpeting with whatever else it's in contact with. Usually carpeting's a relatively better conductor than rubber on our shoes.
So I'm trying to, so when you, like if you got socks on, you don't feel zapping on your feet, but you feel zapping when you touch somebody. Why is that? Is it releasing?
Well, because once charge gets on your body, pretty good conductor, not a great conductor, but charge, once you have a net charge, it'll spread out as far as it possibly can. Now, if there are reasons where it can't spread out too much, it won't, but if there are places where it can spread out, it will. So if you touch something, now you allow a conduit for that charge to go somewhere else. Now, you don't feel the zap from your foot unless you're doing this simultaneously as you're trying to touch somebody, right? Usually we scuff first and then we touch. And so it's at the point of contact where that charge transfers that you'll get the zap.
But if you touch someone with your foot, it would zap.
You betcha. It would zap them as well.
Well, isn't it kind of, you're slowly picking up charge as you're rubbing your feet, but it's
Oh,
all
yeah.
at once when you zap somebody?
Absolutely.
So that's sort of the difference.
And it depends on a whole lot of other factors that aren't necessarily quite so simple. Kind of like a battery. We all walk around with a certain electrical voltage or potential, and how that potential or that voltage compares to anything else around us that we touch will determine whether or not the charge flows off or flows back, or not at all, or to what degree. And the ability to do so depends on a lot of things, including how well the point of contact can physically conduct electricity or not. So there's all kinds of additional considerations that can sort of add to the process. But ultimately, if you've got a net charge and you touch something that has less net charge, the charge is going to distribute just like a gas would from its high density region, spread out to as far as it possibly can to get away from all of its neighbors because of this electrical repulsion. So that's charge by contact. And by the way, there is another one that doesn't necessarily involve contact, but it's now quantum in nature. It's called tunneling. You take two surfaces, have charge on one side relative to the other, bring them close enough together, and have the charge, or the electron, if you will, physically pass across a gap that it should not be allowed to pass across. Quantum mechanically, quantum physics, it's allowed. Newtonian, how we look at physics specifically, it's not allowed, but it still happens. So part of the reason for why we've developed these new model physics is because our existing paradigm didn't work very well. It worked for some of the big stuff. When you start looking carefully, everything continues to change. It becomes more and more complicated. And frankly, we don't know the rules. We're just sort of finding each new observation and trying to make it up as we go along. Now, so there is this whole tunneling thing, but I'm not going to talk about that because that's completely out of the context of this textbook. But the third possibility is what's called charging by induction. This is kind of a cool one. And in a way, it's sort of related to the idea of tunneling. So, here's how it works. say you have two balls here, they could be steel or whatever, and one of them has an excess of electrons. If you bring this object closer to the second object, those excess negative charges are going to do two things. First of all, what is every substance, every atom composed of? One atom, and this negative charge, this positive charge, right? Well, part of the reason for all the chemistry we see, part of the reason for charge separation and transfer, all these things, happen because these electrons are in this space and they're kind of moving around. They're not as fixed compared to what's at the center. Fluid, if you will, in some sense. So when you bring an extra negative charge here, it's going to tend to do two things. It's going to repel due to this negative charge in the atom that's already there, and it's going to simultaneously attract to the nucleus. Now, if it repels this electron, which might sort of on average be located here but just sort of spread out everywhere, it's going to push that electron a little more to this side. Why? Because of this Coulomb force. Now what do you have? Now you have a situation for the negative charge being closer to the positive, or more attractive to the positive charge, because the negative charge has pushed itself over a little bit. We call this a polarization. In chemistry, you may have heard the term electric dipole. Well, electric dipoles exist in nature on their own just by how different atoms, kind of like friction, some attract more and some don't attract so well to their own electrons. So it sort of happens in nature like in water. However, even if a substance isn't polar unto itself, putting a negative charge near a neutral atom, whether or not it's a conductor is irrelevant, will result in ever so slightly disturbing and pushing away the same sign of charge, and ultimately leaving a more exposed opposite charge for that charge to interact with. Consequently, you get a stronger force of attraction for that negative charge, drawing it closer, and at the same time keeping this, or inducing this separation of electric charge. So this intrinsic property is referred to as polarization, or charge polarization. In other words, you create this negative, positive separation of electric charge, but they're equal and opposite, because it's still within the same substance. Now, if by chance, so if we were to do this, then what we would end up with is either one of two situations. We would end up with a bunch of atoms in this neutral sphere, polarizing with pluses and minuses, and I'm drawing this small, sorry. Now what does that polarization do to all of its neighbors? Does the same exact thing. Now the degree to which these polarize their neighbors inside will just depend on the particular substances. But you ultimately end up getting this separation all the way through for all of these, and even on the other side, it becomes more negative on the right and more positive on the left, just because of this cascading domino effect, if you will. So one side becomes ever so slightly more positive, one side becomes more negative. You've induced the polarization of an entire object, maybe to a large degree or to a smaller degree, just due to putting a net negative charge or a net charged object next to it. Now, this would be a non-conductor or an insulator where the positive negative charges are held tightly. This would be an example of an insulator. Now the alternative would be if the non-charged neutral ball or sphere, I'll bring my own negative charge here. The conductor. One thing we know about conductors like metals is that there's at least a proportion or a fraction of the electrons that will flow readily. due to electrical disturbance. Right? That's why we have wires. That's why we can use a battery, attach wires, and get the electric charge to flow. Well, this becomes a more extreme case when you have a conductor. Like a metal. In this case, literally, you push the electrons to the opposite side, exposing some of these atoms as being a little more positive. Now, how much do they spread? Well, it depends on the interaction, how much charge is here, how close they are, and how attractive these electrons would otherwise be to their neighbor, to their parent atom. So you get a separation of charge by induction, but here's the key. If I were to take a wire and attach this to some outside environment that doesn't have as much density of negative charge here, guess what's going to happen to this charge? It's going to flow out. And if it flows out, now somewhere down here you've got the excess negative charge. You still have the positive charges here because of the excess of electrons. If I remove the wire, those electrons are gone for good. And the electrons that are still present here will space themselves out in such a way, that the whole object itself has a net positive charge. So in other words, you just push the electrons, you separate them, and then you allow them a way out of the system itself, and then you remove that pathway so they can't come back. That's charging by induction, or that's separating charge by induction. Now note that you don't have to have a metal in order to get charges to separate and move around and to flow. Even insulators do it. The question is just how tight are the electrons in the atom attached to their own nucleus. Now, that's a very easy way of saying I don't know what happens on a macroscopic scale because every single system, every single atom, every single molecule of substance is a little bit different. So you can't necessarily build a general rule for how every little thing works because every atom is different. But at least the mechanism we can establish as being relatively simple and redundant. So to this end then, today what we're looking at is just going to be how these arrangements can occur using a charge sensor and measure it physically. Have you guys, or either or all of you, used the Logger Pro software with physics lab or chemistry lab at some point? So at least one. Good. As long as somebody has in every workstation, otherwise they want to at least spread out for a first week, just so, because at least the majority of students have been using this all year. There's a whole bunch of features with our software today that are I think learning curve. Just gotta figure out what you can do and you can't do with it. So that's my spiel. So what I'd like you guys to do is go ahead and get a kit and obtain a charge sensor from inside your the electricity bin. There are, I think the instructions are pretty explicit.